Hello and welcome. My name is Dave Davis. I am a consulting acoustical engineer. I gave this presentation as a technical talk at a meeting of the New South Wales division of the Australian Acoustical Society at the Sydney ACOM office on Wednesday, the 26th of July, 2023. In this presentation, I describe a methodology that I have developed over the years during my experience undertaking environmental noise modelling projects. I have been very lucky in my career in that I have worked on a very wide variety of projects all over Australia and the world. I've done environmental noise modelling for lots of different types of projects in many industries of all shapes and sizes and at all stages of project development, from feasibility studies and environmental approvals, concept design, detail design, through to the construction phase and the post-construction phase. I've been very fortunate to have had the opportunity to work on large and small projects with a wide variety of people, including scientists, engineers, architects, project managers, cost estimators, and lawyers, and also with a wide variety of clients from all types of industries and from all walks of life. In that time, I've done a lot of noise modelling and I've reviewed a lot of other people's noise models. And I've realised that my approach to noise modelling is a bit unusual. In this presentation, I would like to describe the way that I do noise modelling, and I would like to share a few examples that demonstrate the value and the usefulness of my approach. Unfortunately, on the night, we missed the first few slides of the recording, so I have re-recorded those first few slides. I have structured this presentation by firstly giving a general overview of my approach to environmental noise modelling. In the introduction, I will attempt to give a summary of the core idea. And although that introduction has several parts, really the core idea is the combination of those parts. The introduction is actually what I want to be the key takeaway of this presentation. Some of the concepts that I will describe in the introduction will probably be a bit new. Some of them might be a bit weird, and at first it may not be clear how those things relate to environmental noise modelling. However, I ask you to please bear with me because I promise that they will all come together and it will all make sense at the end. We are going to talk about problem solving. We are going to talk about engineering and design, how they are similar and how they are different. We're going to think about what noise modelling, what modelling actually is. And we are going to have a very quick introduction to systems and systems thinking. The combination of all these things in the introduction are what makes up the core idea. And that's what I want to be your key takeaway for this whole presentation. So I'm really only hoping to share one main key idea in this presentation, and that's what the introduction is a summary of. But then I will try to cement your understanding of this key idea by giving some examples. Hopefully the examples will do a good job of demonstrating the main idea. And then, after seeing the examples, it is my hope that the core concept really clicks for you and the key idea makes perfect sense. So let's start off briefly by talking about what problem solving is. So I'm an acoustics consultant, and lots of us in the Australian Acoustical Society are acoustics consultants. Not everybody, but a lot of us are. And if we ask ourselves what consulting actually is, well, somebody comes to you with a problem and they expect you to provide the solution. So you, as a consultant, you are a problem solver. In another sense, what a consultant is somebody who takes some inputs in the form of some information and some money and provides some outputs in the form of some information and some advice. So consultants solve problems all the time. There are several different kinds of industries where people solve problems all the time. Take, for instance, the IT industry. If an IT person wants to diagnose and troubleshoot a computer, they have a flowchart in their head, and they use that same flowchart no matter what computer they're diagnosing, no matter what problem they encounter. Every problem they encounter is slightly different, but they use the same flowchart. If you asked that IT person to write down that flowchart, they probably wouldn't be able to do it because it's very vast and complicated. Similarly with the medical industry, if a doctor is diagnosing a patient, then they consult the huge, vast flowchart that they have in their head, and they use that same flowchart no matter what patient they're encountering, and it usually works pretty much most of the time. If you ask that doctor to write down that flowchart, they wouldn't be able to do it because it is vast and complicated, but it works pretty much all of the time. Similarly, engineers, when an engineer is solving a problem, then they consult the vast, complicated flowchart that they have learned, that they keep stored in their head, and they use it pretty much all the time for every problem. And every problem that they encounter is slightly different or very different, but they use the same flowchart for every problem that they encounter. And similarly with acoustics consulting. So we solve problems in a similar way. We have a flowchart in our head that we use to solve problems, and every problem that we encounter is slightly different, but we use the same flowchart no matter what problem we encounter.
Right, okay. So engineering problem solving, they have actually tried to document what it is, what this flowchart is, and they come up with a procedure like this. Is everybody online? Can you mute your microphone? Sorry, people, we had some echo there for a second. Got acoustic people up the back doing their thing. So engineers would follow a procedure when they go through problem solving. Now, if you go looking for what is the engineering problem solving process, you'll find similar kinds of procedure maps like this, you know, several different kinds, some a bit longer, a bit shorter, whatever, but basically there's a procedure that they follow when they're going to do a problem solving exercise. Design people also follow a procedure when they do a design. If you look carefully, I mean, and by the way, if you go looking for what is that procedure, you find variations on this theme, but they basically all follow a procedure, a lot like that. You know, slight different, more or less steps, but in general, that's what they do. Now, those two procedures are actually very similar. Okay, and that means something. But not all problems start, finish, and not all design tasks are start, finish. Some of them go round and round. Some of them never stop. Some of them go forever. Some engineering problems can't ever be solved, so you iterate around it. You keep solving the problem again and again, better and better each time, or maybe the problem is slightly different each time, but it never goes away, and that's your job for life. And design people might also have a situation where they have to keep designing the same thing over and over again. Mobile phones, there's a new one come out every year, so they keep designing the same thing again and again. Now, again, you go looking for that, you'll find slight variations on a theme. You go looking for that, you'll find slight variations on a theme, but they're very similar. What does that mean? Well, you don't find that written down anywhere, but I'm saying it. Engineering is design. That's what it is. When you engineer something, you're going to design something. So engineering is really a design discipline. That's how they solve problems. Got an engineer, so I've got a problem. What do? They design a solution. Okay, a lot of us are engineers. But I think what we do isn't a pure kind of engineering type problem solving. What we do as acoustics is different. I'm saying acoustics consulting is not a type of engineering. It's a bit special. Perhaps your client's problem doesn't need you to design anything at all. So they come to you with a problem. A design of any kind isn't going to solve that problem. Maybe they just need you to prove something. That's different. You're not designing anything at all. But very valuable service though, if that's what they need you to do. So if you were to try and follow the engineering problem solving procedure, it wouldn't be useful to you in that situation if you're not going to design something. These are models. They're quite different, but they are all models. Got a model train set, it actually works. It's a scaled down version of a thing that actually works. It's basically like if you built it up, if you just expanded it to 10 or 20 times the size, it would be a real train system and it would work. And you could do train things with it. An architect's model isn't really something that you could scale up and live in, because it's like the materials that it's made of aren't perfect, and it's a concept really, but it's a physical thing. In general, it looks a lot like the real thing's going to look like, but not perfect. If you draw a thing in cyberspace, if you draw a bridge or a building or anything like in an electronic CAD program, like whatever, and not necessarily give it any properties. So this is not necessarily a physical model in cyberspace. This isn't like a structural stress or strength type model. This is just a drawing in 3D space. But that's a model. And that's a very nice one. That one might actually even float. Okay? But these are also models. Molecules don't look like that. Molecules don't actually have rod things that hold the molecules together. But when we look at that, we know exactly what it is. The chemist looks at that and knows exactly how it works and how it fits together and why it's shaped like that. The chemist knows that the rods aren't real, but it's still an incredibly useful model. This is a model. This is an abstraction of the human body. They have made no attempt at all to try and make that look like a real human being. They don't need to, they don't want to. This is a model of the human body in terms of vibration. Okay, it's very good for that purpose, but only for that purpose. So it's an abstraction, but it's a model. It works very well. If you go, if you go to a cardiopulmonary surgeon and say, is that the human body? They would say, no. Go to a vibration person, you say, is that the human body? They say, yes. So it's a very useful model, but not for everyone, only for vibration. That's a model. If you show that to a mathematician and you say, is that a model? The mathematician would say, yes, that is a model. Absolutely. And that's what they think of. If you ask a mathematician, model this for me, that's what they come up with, bunch of equations. To them, that's what a model is. Not a drawing, not a physical thing. It's equations. These are also models. That's Copernicus's model of the universe. It's very wrong, but it was a model. And for a while there, for some people, that's all they had to work with. That's a model. E equals mc squared. So that famous equation, that's a model. Okay, so what I want you to do, please, after seeing those things and having your mind thrown all around the place, what is a model? Now I don't know what a model is. I want you to change what you think modeling is. I want you to change your approach to what you do when you do noise modeling. And the reason why I want you to do that is because you're going to change the results that you get out of it. Okay, so what is a computer noise model? When we do noise modeling, what are we trying to do here? Are we trying to build our noise model to make it an absolutely perfect simulation of reality? Are we trying to make an electronic copy of the world in our computer modeling, in our noise modeling software? Do we want our models to basically try to be perfect representations of the real world? Or is the noise model an abstraction? Does it need to have every part perfectly defined, or can you just define what you need to and get a perfect answer? Well, I know which one I think it is. But anyway, as with all models, with computer noise models, it's no different. A model is only a model. All models are wrong. There's a really good reason for that. All models are wrong. Some are more wrong than others. Some are pretty close to correct, actually, but they're still a little bit wrong. So don't ever make the mistake of thinking that your models are right, because they cannot be perfect representations of reality. So start there. Whatever I have modeled, it is wrong. Maybe it's only a little bit wrong, but it's not perfect reality. Anyway, some models are useful. That's the takeaway from systems engineering. All models are wrong, but some models can be really, really useful. And that's the key point when you're looking at noise modeling as a systems thing, which I would like you to start doing. And computer models are dangerous because they can be wrong, but it's hard to know if they're wrong. Because if you put garbage in, you get garbage out. But if you didn't know that it was garbage going in, then you might think that it's beautiful, lovely, perfect going, stuff that comes out. Okay, systems thinking. So I would like us to start taking a systems approach to noise modeling. So systems thinking is different from design thinking. Systems thinking happens in what they call state space. So your job as a systems person is to change the state of the model from state 1 to state 2, from one state to another. So if you start off with a problem, then your job is to change the state of that model to a situation where the problem is gone. So you haven't really performed any magic apart from changing enough in the model from the situation where you start to where you want to be. So a system is different from a design type project because a system is not a process. Okay? With a process, you start, you do stuff. Maybe it's got some iterations in there, but basically you finish. That's a process. That's like a design type procedure, like an engineering problem solving type procedure. You start and then you finish, right? Maybe you go around and around again, but basically that's a process. But your noise model can be more than that. Your noise model can be more like a system whereby you have a collection of parts that are all interacting. So you're not actually, when you do your noise modeling, you're not designing something from start to finish and then you go, okay, I'm finished, I've done my noise model. No, now that you've got a noise model, now you can work with it and do stuff with it. So a crash course on systems. What is a system? It's a collection of interconnected and interacting parts. The whole is greater than the sum of the parts. So a system will have an emergent behavior that none of the individual parts can have. Together though, you get a completely different set of behavior to any of the individual parts. A system has inputs and it produces outputs. This definition is common to all systems, by the way. If the inputs change, then the outputs will change. That's important. That helps you define your boundary, by the way. If the internal parts change, then the outputs change. A system has, so we just talked about what a system is. A system has a boundary. It has inputs. It has goals, or maybe one or more goals. What it does is processing. So the stuff that comes in, it processes the stuff that comes in. And what it produces is the outputs. And you don't need to define the rest of the world. You only need to define your system's boundaries, the inputs and the outputs. Don't bother trying to model everything else. You can't. This is an example of a system. It's a collection of interconnected and interacting parts. The whole is greater than the sum of the parts. A system has inputs and outputs. There's your inputs, outputs from the speakers. If the inputs change, the outputs change. If the internal parts change, then the outputs change. Okay, that's a sound system. There's a reason why we call it a sound system. Okay, but you cannot actually model a system. That's really important. The reason why is because a system, it has an infinite variability of definition, and where do you stop? If you wanted to try and model a system, you need to know where to stop, right? So you can't model an entire system because the amount of detail you need to put in it is infinite. So don't try. You can only model a problem. Okay, so the first thing you need to do is define the purpose of your model, and the second thing you need to do is define the boundaries of your model. And what is the purpose of your model? That helps you define the boundary. And what is the problem helps you define what the boundaries are, and so on. Don't model more than you need to. Don't try. Just put just enough detail into your model as you need. No more, no less. You're only trying to model the problem, not the system. So here's our two kind of examples of what we kind of typically do in acoustics. Somebody wants to build a thing, doesn't exist yet. The problem is that it doesn't exist yet. They want you to help them solve that problem. Help us make it exist, right? Build it. So you change the problem, you change the state of the system from state 1 to state 2. Make it help us make this thing exist. Fine. How about if something is just too noisy? Problem, it's too noisy, right? Your job is make it okay. Now wait, what do I mean by that? I don't mean make it quieter. You just solve the problem. You don't necessarily have to change anything in the system. Maybe it's just a case of you just analyze something, you find out, oh, actually, you know what, if we look at it like that, there's no problem. So your job is not necessarily to fix the thing that's too noisy by making it quieter. Maybe there's another way. Okay, so let's jump into some examples. By the way, that was the good bit. That was the takeaway that I want you to take away. That's what I want you to start thinking of your noise model as a system rather than as a design process. So some of these examples might not be surprises to some or many of you in the room. I hope that at least one of them will be a surprise to all of you in the room. But I've found over the years a surprising number of people who haven't thought of this, so here I am sharing it. What if you have a slowly moving noise source, like a construction project that's going to take a long time to build something that moves? So it's a linear infrastructure project, and it's going to take months and months to build the thing, and the construction fleet is going to move very slowly. Okay. Now, somebody says, well, what's the maximum noise level that we're going to receive over here at our receiver? They don't mean the maximum noise level. They don't mean the Lmax. They mean the maximum LEQ. So when they're working around here in April, May, what's the maximum, say in New South Wales, we do a 15-minute thing. So what's the maximum LEQ 15-minute that they're going to experience at this house from this construction fleet? You trick the noise modeling software. You trick it. You force it to give you that answer. The noise modeling software doesn't want you to have that answer. It's not designed to give you that answer. You can make it give you that answer by hacking it, so to speak. You put your LEQ sound power level into the Lmax input box. And you tell the modeling software that this is a moving point source, and you don't care how fast it moves. And if the software wants you to give it a speed, then it actually doesn't matter. You don't care. That's not the answer that you want. You take the predicted Lmax from that software as the maximum LEQ. Simple as that. And then you can add and subtract and whatever those results if you want. You can turn those into contour maps if you want. You can add and subtract the maps from each other. But you have now got a way of predicting. You don't know when or where the noise sources were when they produced that maximum LEQ at that receiver. And you don't care. That wasn't the question that they asked you. We can find that out some other way. But if they just want to know what's the maximum, yeah, you can find that out. And this is sort of the difference. So if you model the noise source as like a normal LEQ type noise source, you get the 3 decibels per doubling distance from a line source. And so you get these funny shapes around the edges where the near field effects and stuff. And that's wrong. That's not going to, that doesn't actually give you the answer that they need. They want the maximum LEQ of any 15 minutes as the noise sources move from there to there. And they don't care when or where those sources were. But if you trick the software and you put the LEQ sound power level in your Lmax box, you run it like that, and you tell it that the total sound power is located in one point, and then the software realizes that it takes some time to move from there to there, and you don't care, right? Because that's not your answer. You get 6 decibels per doubling of distance from a line source. That's the right answer. So over here at the receivers, you don't know when or where the source was when you got the Lmax there at that point. And you don't need to, because that's not what they asked you. So this is like, now that your model is a system, you can change the parts that's inside the system and get a different answer. You don't actually have to answer the question literally. you can say to yourself, well, I'm going to do some problem solving by looking at my system, looking at the parts. Maybe I'll chop and change them, turn some inside out, take some out, put some in, turn them upside down, whatever. But let's just turn our noise model inside out. Okay, so this is a reverse noise contour map. Why can't you do a noise contour map inside out? Say you've got a site where you've got construction or noise sources moving slowly over the site. This might take a year or 2 or 3 or whatever to build this site. It might be huge. Now, you can do what I just showed you, where you say the total sound power of this construction fleet is located in one point. Okay, give me the L max over here. Well, actually, no, just give me the L max everywhere. And I don't care where the source was. Or you could swap the source and the receiver. For each receiver, you could swap them. Make your receiver the source. Make your source the receiver. You flipped your noise model inside out. Now you know where the sources were that gave you the L max noise, the maximum of the LEQ noise levels at the receiver. So over here at this receiver, you would want to concentrate your efforts around here to try and reduce the maximum noise level that receiver ever received. Okay, so here you don't know where the sources were that made the maximum noise level that those receivers received. So if your client says, well, now I've got a problem and you're not helping me solve it, where do I have to pay attention and where do I have to produce my noise sources so that I comply with my criteria of my receivers? This is how you answer that question. So let's say the criteria that this receiver is green, okay, 57. So now you know that from there to there, you've got to do something about the noise sources in that zone for that receiver. Speaks for itself, really. Transfer functions. This is a systems idea. It's a control idea. I remember it from control systems at engineering school. But we can use transfer functions. I mean, if you think about what we do with acoustics, we've got a source in decibels. We've got attenuation from between the source and the receiver, and those attenuations are a combination of many things like ground absorption, air absorption, barrier shielding, and so on. And some of those things even actually interact with each other. So if there's weather, then that reduces the effectiveness of the barriers and so on. But each of those attenuations from the source to the receiver is like a gain. Okay, like on the sound system where you turn the volume dial up, then it's just a decibel gain, right? So a gain can be negative. That's an attenuation. So each of these attenuations between the source and the receiver is a negative gain. It's an attenuation. So think of it like that. Everything between the source and the receiver is the transfer function. So you don't actually know how much is which and how much attenuation is from the barrier and the ground absorption, and you don't care. You don't care. It's just all the transfer function between the source and the receiver. So put a dummy noise source into your source. Put a dummy spectrum. Nonsense. 100 decibels, whatever. Doesn't matter. You're not interested in the sound source. This is why it's valuable to stop thinking of what we're doing as a design process, because now we don't even have to have the source right. We just want the insides. We're just interested in the insides. We don't care about the source. We want the transfer function between the source and the receiver. So you calculate the difference. Start with your dummy noise source. Don't forget what it was. Calculate the received sound pressure of the spectra at your receiver. The difference is the transfer function. That's going to be the same no matter what the sound power level of the source is. Very valuable information. Now you can work your magic. Now you can take that number and you can pull it into your favorite calculation tool like Python or Microsoft Excel or something like that. And if there's some formulas in there that have been pre-populated into that tool that you trust, like if you use a calculation tool in Excel like Strut or something like that, then you can go ahead and do heaps of calculations very, very quickly outside of your noise modeling software. You took the guts out of the noise modeling software, and now you can play around with that very quickly. Do lots and lots of optioneering and what-if scenarios in your Microsoft Excel software, or Python or something. So you've got a source and some receivers. The transfer function is the blue. That stays the same no matter what happens to the source. In each band, of course, we're talking about frequency bands here, so just keep that. We're all working in frequency bands, so we know what we're doing. But that's constant, and so if your criteria is here, then you know how much you need to reduce the source by to make sure that you get compliance at all your receivers. Do this calculation outside of your noise modeling stuff. You don't have to keep running the noise model over and over and over and over and over again. You can just get the answer outside in Excel. So the same concept now. Say you're designing an industrial building that's got some noise sources inside it, and you've got a receiver somewhere else, and you've got to try and design that building to keep the noise inside, right? You know, basically, the client's told you how big the building's going to be, but they aren't telling you what they want to make it out of. That's your job. You tell them what they should build the walls and the roof out of to keep the noise in, right? So you build it as an invisible ghost building. You build your industrial building with acoustically transparent walls and roof, zero transmission loss. Now you've got the transfer function now. So the transfer function between the source and the receiver is the same no matter what happens to the source. Right? You've got the transfer function between each of these sources and the receiver. Don't care what the sound power, the transmission loss of the walls are. I mean, yes, you have to make a decision about the internal absorption, but that's, we do that. Still, now you can go and flick through a very large number of options of what to build that building out of outside of your noise modeling software. You've got the good stuff out of your noise modeling software. Go and do your magic in Python or Microsoft Excel or something, using Struct or something like that. So what's to stop you now having a huge database of transmission loss and stuff? You don't need to go back into your modeling software and keep changing the walls and the roof over and over again until you find one that works. Do it in Excel. Hopefully this isn't such a crazy idea. So let's say we have a large noise source. It's common practice for a lot of these manufacturers to give you information of the sound power level in terms of a sound pressure level at a distance. That's annoying, particularly because people who aren't acoustics people will then think, oh, I know that equation, I learned it in school, and they do the point source thing. Okay, that's wrong for a large noise source. I've seen that done wrongly many times. I'm sure you have too. Don't do that for a large source. Okay, maybe we don't need to. What else are you going to do? Well, this complicates things. Like if you want to actually back calculate this stuff and try and figure out what the sound power level of each panel is going to be using the fact that, up close to the surface of your area sources, you don't actually get any attenuation at all for a little while. And then for a little while, where it's basically like it's propagating like cylindrical propagation away from your source, like a cigar-shaped kind of propagation, you'll have like 3 decibels per doubling of distance. And then when you get far enough away, now it starts behaving like a point source. But if you start here and you assume that it's a point source, that's how wrong you are. So if your source is large, don't just make that mistake. Get your noise modeling software to do it properly, quickly and easily. You put in a dummy noise source. You don't know the sound power level of your area sources of this large area of your whatever it is. You don't need to. Put in a dummy sound power level. Put in 100, whatever, a dummy number. You don't care about what it is. But they told you what it is at 7 meters. So whatever number you do get from this dummy noise model, the difference between that and 59, that's what you adjust your sound power of your source by. Now your sound power of your source is correct. And you don't even care what it is. That's a quick, easy way to figure out, back calculate what the sound power level of that source is when you don't get the information given to you as a sound power level. You get it in the sound pressure level at a distance, which is wrong for a large source to assume that it's a hemisphere. Yeah, so there we go. Same again. Sometimes I'll give it to you at 1 meter, which is even worse. But why not just build a model like that and say, okay, we'll put a receiver at 1 meter. Now you can do what I just did and back calculate what the sound power level of that's going to be. And it works. You don't have to do that. There we go. So that's it. That's my examples. So I guess final thoughts that I'd like to leave you with. Noise modeling software is not just a design tool. Okay, you're not necessarily stuck with just the one mode of doing anything in noise modeling. You're not just there to design a solution. Maybe you can come to the solution without designing anything. If the noise model is, if you're thinking of it like it's a system, then your noise modeling software is suddenly, it's a very powerful problem-solving tool rather than just a design tool. So hopefully I've explained that well enough. Yeah, please just change the way you look at the things, and that means that the things you look at changes.
Do we have any questions?
I'd like to make a bit of an observation, Dave. When you had your emergency diesel generator, of course, you're assuming that the sound is going to be constant at 7 meters all around your generator, which of course is completely incorrect. You have air intakes and exhaust pipes and stuff. But I mean, I know you're using that as an example of a big area, a big source. So
I had the same thought, and I realized that if a client gives you this kind of information, or if the manufacturer gives you that kind of information, they should be giving that to you correctly, which is an average. So
they typically don't. They typically measure the noisiest.
Which did they measure it? Let's see, this is my scribble to my person I was working with. Where did they measure it?
Yeah,
was it there? Was it there? Different answer. You know, if you just assume it's an average, I guess you can go off and work with that. And if they make sure that, if they assure you, don't worry, that's the direction that the receiver will be. Yeah, trust me. Then you've got your protection, I guess, to make that assumption and make it clear. Yeah, so I guess don't try this at home. Well, actually, I do. I want you to try muck around with your noise models. Like, so these are only 5 examples. They're just quick, simple ones. I'm not claiming that these are particularly amazing, but like now that you're thinking of your noise models as a system, and you think you're free to muck around with them more than you used to be when you thought they were a design tool, I'm sure you'll come up with your own tricks and stuff like this. And you know, when you do, please share them with the whole group.
Thanks. Yeah, that's all right.
Can we use the microphone because we've got people online?
No, it's online, so that
Thanks, Dave. That was really good. And I'd like to reverse contour one of the and across my mind before that. I just wanted to say you mentioned strut, and strut. If anyone, what's that? The risk of sounding like this is a plug. If anyone is interested in knowing more about strut, it's an tool, and happy to answer any questions. At the end of the commercial.
Anyone want to see anything again? You want to backtrack in any particular one you want to talk about at all? I do. Well,
So your question about changing the location of the source and receiver. So just wondering how you like. So you're saying if you change location, you can sort of then backtrack to figure out for that particular receiver where the noisiest source could have been. Sort of thing.
That's right. That's the point. So now if you know, well, say you did this calculation, you go, oh, well, I'm exceeding by decibels, right? What do I do about that? Well, you come here and you go, well, that means I've got to treat wherever that exceedance is. That's from there onwards, I've got to do something about it. Like don't do work at night time there, like that kind of thing. Or, you know, make the dozer only use first gear in reverse instead of second gear. That kind of thing. That's now you know where to focus your
where
efforts
your
to.
problem place is.
So Dave, does the reciprocity work if you've got temperature
No,
inversions?
of course.
And
No, never show this. Never show this to your clients. This is you using it as a problem-solving tool. Okay, the equation, the maths here is wrong. These numbers are not right. If you reverse your source and your receiver, that's the formulas are not right. But it's still useful. That's the point. All models are wrong. Some are useful.
We have a couple of questions coming online. We have from Joel Harry Jones. Says, thanks, Dave. You mentioned about your experience in many large, small firms. How often do you find you need to educate junior or even experienced consultants about problem-solving techniques?
I don't. I keep them to myself. But I teach the people that I work with. I teach them as whenever the need arises. It often just doesn't occur to me that I could teach the people that I work with other tricks. I just, you know, whenever we're doing a project, then I go, oh, I could use that trick. Like this isn't all. I've got more tricks than this, but I haven't sat down and taught a big lump of them like this to anyone. Not my people or, you know, the society.
Okay, then we also have from Rod. Rod, please feel free to unmute and ask yourself if you want to. He's asked, first of all, is there any particular software being used for these insights?
I have used SoundPlan for these examples just because I'm more familiar with SoundPlan, but I have also used Cadna for years and years. I would say one is probably better than the other, depending on the situation. These days, before I start anything, I look at the problem and I pick whether I'm going to do it in SoundPlan or Cadna. But honestly, seriously, you don't necessarily have to tell the client that you did this, but you could model it in both and compare them. And if you were working with a wicked problem, then maybe you need to do that to figure out what's going on, because I mean, they are different. In a broad brush sense, they should be very, very similar, but yeah, little quirks of their algorithms and stuff might reveal things that the other one didn't show you. So yeah, don't be afraid to model it twice.
It's similar to what we've known that sometimes consultants get asked to model in different algorithms. So the ISO or Concawi or something, and do both for the project. Is that something you're familiar with or would endorse or over the top, crazy,
no.
silly?
If you're using your noise modeling software as a problem-solving tool, then you shouldn't be restricted to that. I mean, the final output, the report, the one that goes into the report, sure, you've got to use the method that they have insisted on. Right? But if you're actually investigating what's going on inside your model, yeah, don't feel that you are stuck with that one. Change and see what the other one does. And, try and figure out how it's working inside, playing around with the maths. Like, see the ISO or the Concawi or any of the others, like those algorithms are simplifications. They are abstractions. The maths in those formulas aren't right. I mean, it's wrong, but it's wrong to a small degree. But they're different. And like just barrier here. I mean, if the wind is blowing that way or that way, it's going to change what happens, right? Maybe it'll change more using Concavi than it does in ISO. In which case, now you get starting to understand it's actually more important. So, for instance, like with this one, don't show that to your client. Don't tell them that's what you did. But it might be more valuable. Like, say you have to use Concavi for the real problem. You don't have to use Concavi for this problem. You can use ISO or something else. Jeff?
Dave, is that working?
Yeah.
Okay. Dave, thank you very much for that. I think, you know, sharing your tips and your tricks and rules of thumb has been really useful. I think that's helpful because
you understand the models that you're using. In 20 years of being a regulator, I've seen some other people who've, let's say, magicians, and they've been using models, and they've been coming up with numbers that, yeah, they're magicians. And one of the things that is a problem there is that they use models, but they don't really know how they work properly in the first instance. And an example that used to come across my desk a lot was someone using Corton to model construction traffic, like coming up slowly out of a work site up a hill. So they had a model that was designed in the 1970s in England for fast, free-flowing traffic with 5% trucks, and then they apply it in Australia to trucks going from 0 to 10 kilometres an hour out of a construction site, and they come up with magical numbers. So I think one of the takeaways, and this is more a comment, is these things work fantastic, but you really do need to know how your model works and the basis of it and how it's developed before you try some of those tricks. And if you've got a comment on that, that'd be great.
My comment would be that whoever that is, they got paid and they achieved their client's goal. They made the problem go away. But I know exactly what you're saying.
I wouldn't suggest that.
Exactly.
It was my job to make sure it didn't get away. Sorry to spoil their little magic show.
I fully agree. Yeah, I am an idealist and a perfectionist, and I do need to know what my model is doing before I am comfortable telling anyone what it did. I wouldn't want to put out an answer unless I knew what the software was doing. And if I didn't understand it, I would interrogate it until I did. And I think if I was going to deliberately deceive anyone, I would make sure I never got caught. But the point is extremely valid. You need to know what your model is doing. And I think this is important. You don't need to understand vibration as well as the person who came up with this in order to use this model. Okay, you can learn an awful lot about the maths of the vibration of the human body just by having one of these to play with. And you will eventually get a feeling for the maths of the vibration here, but it takes time. And the way to develop that understanding is by playing with your model, playing with the software, experimenting, pull it apart, change stuff, make stuff go up and down, large, small, knowing full well that that will never be one of your outputs. I mean, if you want to understand your model, you need to go beyond the scope of just treating it like a design project where you go start to finish and I'm done. Right? That's not noise modeling. See, my view is that your noise model, a lot of people think that noise modeling is building the model. So you start, and I'm finished. Now I've done my noise modeling. Press go, I'm done. And like while they're building this, what are you doing? I'm doing noise modeling. No, you're not. Noise modeling starts when you're finished building it. That's when you can actually start your modeling. After the model is finished, being built, that's now you can do noise modeling. The rest of it is just building the model. It's not modeling. That's my view. Once it's a system, then you can understand the model. That's modeling. So I don't necessarily think that it's entirely required to understand the model, but I do think it's important to have done so much modeling and playing with modeling that you understand how they work and what's important and what's not, and so that you don't let the model trick you.
Maybe what I'd say is at least know the limits of your model.
Yes.
Okay, we just had a couple of online questions. Angus, do you just want to grab those couple there?
Yeah. So I'll just, who's got
Microphone?
Yeah, sorry, can you hear me?
No.
Yeah, none.
Okay.
Sorry.
Can you hear me now? Yeah. Perfect. Cool. The other question, so I'll just go in order. Also on the reverse contours, this is similar to one of the other questions. The reverse contours, could you clarify why the effects of shielding, buildings, barriers don't cause different patterns of propagation when the source and receiver locations are swapped? So I think that's probably just further clarification on some of those factors.
Well, this one, the source is actually everywhere all at once. This is one of those calculations where you let the noise source be everywhere all at once, and the software takes the maximum of those. At every receiver calculation point, the software will say, well, I don't care where the source was, I'm just going to take the maximum answer, and that's the answer. Why you don't get the same answer to this one is because you've only got one source. So if the source was in any of these locations, then that's the answer that this receiver would get. So this map is correct, apart from the fact that the wind is blowing the wrong direction and the barrier shielding will be wrong. But in a general sense, that is the noise levels that you would get when the sources are at any location, any of those locations. Whereas this one, that's a standard calculation that you never find out where the source was to create that noise level right there or there. This is how you find out.
Okay. Yeah, hopefully that sort of helps. Second question is a bit different. So I've noticed the examples mainly deal with airborne sounds. Are there any software models for, say, structural, for example, how vibrations from one room transfers through to structures to cause noise in another room? So in terms of, yes, other modeling sort of situations that you've sort of looked at and where you could apply this. Vibroacoustics models are an even better example for considering your model as a system. They are, it's a no-brainer, it's obvious, I would say. Vibration through a building, converting into sound, that's almost the very definition of a system. Anyway, I would use VA1 if I had to do that. Thanks. I think that probably helps. And another question: any examples of environmental noise models of the non-computer variety? So I'm not sure whether that... Well, Corton was never meant to be computerized. It was a book that you had in the field with a clipboard, and you had a ruler, and that's what they did because they didn't have portable computers. Corton was never meant to be converted into a computer model. It was only ever meant to be used in the field by someone with a clipboard. So surely that's like a model. There's others like that too, sure. I think I saw a Ready Reckoner once a long time ago back in Queensland. It's like, one of those circle things with the transparent thing that you wheel with the calculator. That's a model.
Okay, I think Claire's dropped off.
One more question.
There's a couple more in here though. Glenn?
Can you pass the microphone over this way, pretty please?
Can you grab the microphone for Glenn? Oh, Glenn, you're on this side of the room. You can probably be picked up by the microphones anyway.
I'd like to follow on from Jeff's comment about modelling accuracy. I think we have a real problem in our industry of people not understanding that the models are fundamentally inaccurate. We've recently reviewed a number of reports for a council for various DAs. The modelling has been terrible. People just haven't understood the very basics of what they're trying to do, let alone accept that their model is fundamentally inaccurate. You don't have to understand the workings of the maths. You just got to test it. You just got to think about it. And I think as an industry, we have a big problem, especially now that prices are coming down as consultants, and we're kind of competing against the lower rent consultancies who just don't have a clue. And it's all to do with the garbage in, garbage out, but it's a model and it looks good. And so I think as an industry, we have a real problem about modelling for that very reason of it being inaccurate fundamentally.
That's one of my motivations for preparing this and presenting this. I've been similarly frustrated. And see, I saw it so often and there was so many commonalities that I realized what they were doing. They thought that modeling is building the model and you just design, you just draw stuff like a CAD model, you just make sure you draw it perfectly and then the answer is right, isn't it? Well, no, there's so many ways that your noise model could calculate so many different things. But yeah, sure, the physical objects in your model kind of represent reality, but that's not the point. That doesn't mean the answer is right. That's what I wanted my introduction to really hammer home. You don't need it to be, you don't need the physical structures in your model to be accurate. Only model in as much detail as you need to get the actual answer. So you need to solve the actual problem. Maybe you don't need to build any buildings at all as receivers. Maybe you know, once you start looking at your noise model as a system, you suddenly question, well, what don't I need? Maybe I don't need half of the stuff that I normally put into my model at all. It's not adding any value. So leave it out. And then play with it, see if you can understand it. Put stuff in. Didn't make any difference. Didn't make any difference. I don't. You can understand what's going on.
Just building on example 5 and understanding the model. One of the things that I'd really love if anyone had any tips on was establishing what directivity to apply for area sources on industrial buildings, or we kind of understand what a stack does, but what does a louver and a wall do? Are we just applying 3 dB hemispherical boost? Is it 9 dB on axis? All of these things, like when you're doing the back calculation, I'm kind of slightly in the dark on what's most appropriate.
Well, Strutt's got what's his name? Lehman Miller. Hey, I would love to borrow a copy of Lehman Miller. That's my chance. I cannot get a copy of it, but I would love a copy. If it's Perry or someone just lend me for a while, please. I'd love a copy of Lehman Miller. But that had some good louver directivity, I'm pretty sure.
Lehman Miller's just, I think Lehman Miller's just the stack directivity, which.
No, it's a whole book.
Oh, okay. Yeah.
I think they also had a louver directivity there. Correct me if I'm wrong. Anyway, Strutt does have a louver directivity. Strutt does have a louver directivity.
Yeah, but it's not in sound.
If you need something and it's not in the noise model, go to a book. That's just, the noise model is one of your tools. Yes, absolutely dead right. When was the last time you opened a textbook? Excellent. You win. Go to the head of the class. Seriously, read more books, please. Have we all had enough? We had enough?
Well, Dave, on behalf of the Acoustical Society, thank you very much for sharing your tips and tricks. Very generous of you. Appreciate it.